Building an AI model is only half the battle. Evaluating it is where things get tricky. We have to know the difference between how often the model is right when it speaks up versus how much of the target it completely missed. Let's set up a scenario. You are tasked with designing a medical screening tool to detect a rare disease. This specific condition affects exactly one person in a million. You could spend months training a sophisticated neural network to find it. Or you could write a single line of code that simply marks every single patient as healthy. The system does zero analysis. It just rubber stamps everyone as negative. If we grade this lazy model using standard accuracy, the math checks out perfectly. Out of 1 million patients, it got 999,999 right. That is 99.9999% accuracy. But it completely failed its medical purpose because the only patient who actually needed treatment was ignored. When you are searching for rare anomalies, whether that is a disease, a fraudulent credit card transaction, or a manufacturing defect, overall accuracy hides the truth. To evaluate models like this, we have to split our grading system into two specific targeted questions. Let's look at a different problem, building a spam filter. Suppose you set your filter to be highly aggressive. Over the course of a week, it flags 100 emails as spam. But when you check the junk folder, you find 20 important emails from your boss mixed in with the ads. Those 20 emails are false positives. The model claimed they were the target, but it was wrong. If a system continuously accuses innocent targets, users stop trusting it. They will just turn the filter off entirely. This brings us to our first specific metric, precision. Precision answers one question. When the model predicts a positive result, how often is it actually right? In a standard confusion matrix, to calculate precision, we look at the vertical column for predicted positives. We take the correct predictions, the true positives, and divide them by the total positive claims made. That is, true positives plus false positives. Precision measures a model's credibility. It is the direct mathematical penalty for crying wolf. Now let's try the opposite approach. You make the spam filter hyper-cautious. It only flags an email if it is absolutely certain. It catches 10 spam messages with 0 mistakes. Your precision is a perfect 100%, but your inbox is still overflowing with hundreds of obvious spam emails it was too timid to flag. Those missed spam messages are false negatives. If a model misses a massive portion of the actual targets it was designed to find, its existence is pointless. To measure this, we use the counterpart metric, recall. Recall asks, out of all the actual positive cases that exist in reality, how many did the model successfully find? Back at our confusion matrix, we shift our focus to the horizontal row for actual positives. This time, we take those true positives and divide them by all the real target cases. That is, the true positives plus the false negatives. In practice, data scientists do not do this math by hand. They pass their ground truth labels and the model's predictions into standard Python library functions, immediately generating both scores. Imagine programming a self-driving car's pedestrian detection. Look at this matrix. Is a low precision or low recall score more dangerous? It is recall. Low precision means braking for a shadow, a false positive. But low recall means missing a pedestrian entirely. That is fatal. The decision to prioritize precision or recall always comes down to the real-world penalty. You have to ask yourself whether a false positive or a false negative causes the most damage. In machine learning, these metrics are in a constant tug-of-war. Optimizing one inevitably degrades the other. Lower the decision threshold to make your model lenient, and it catches every target. Recall fills to maximum, but precision drains away. Tighten the rules for absolute certainty, and precision fills up, but it ignores subtle edge cases, so your recall plummets. This graphic shows the final summary. Precision is asking, how sure? Recall is asking, how many? But this leaves us with a structural problem. If you need to quickly compare hundreds of different model iterations, you cannot constantly juggle two competing metrics on a sliding scale. To do that, we need a single mathematical score that effectively balances both precision and recall. That brings us to the F1 score, which we will break down in the next video.